a revered founder chairman, Dr. KCT Burgess, founder chancellor, an insightful contribution.
Led the legacy and the vision.
Good morning to everyone. Distinguished chief guest, respected Nobel Laureate, Professor Moungi, Bawendi. Unfortunately, our Chancellor is unable to attend. As you heard before, there was an urgent inspection by the Government of India in one of our other units, so he had to be away on that assignment. He conveys his greetings and his wishes to all of you and to the august gathering today. Respected Vice Chancellor, Dr. Vikas Mishra, esteemed dignitaries on the dais, off the dais, scientists, academicians, industry leaders, and innovators. Dear faculty members, researchers, students, and delegates from India and abroad, members of the press, ladies and gentlemen, it is indeed a great day at Hindustan Group of Institutions today. Yet again, we have a very important guest and our friends from across the planet. It is with pride and profound pleasure that I address this gathering on the occasion of the International Conference on Quantum Horizons 2025. I extend my warmest greetings and a heartfelt welcome to all of you. At the outset, I would like to express our deep sense of honor in hosting the Nobel Laureate, Professor Bawendi, as a chief guest for this conference. Your presence amongst us is not only a celebration of scientific excellence, but also a powerful inspiration for our students and young researchers who aspire to push the boundaries of knowledge and innovation. I also welcome our distinguished keynote speakers, panelists, advisors, industry leaders, and collaborators who have joined us from across the globe. The theme of this conference, as mentioned by the Vice Chancellor, captures the defining challenges and opportunities of our times. Last night we had a very beautiful dinner for our guests from overseas, and we had a quite an inspiring discussion about where we are heading as youngsters, where you all need to be heading, and the concerns which we all talk about today, the environment. Sometimes when you're with such leaders who does so much for society, it is so important and relevant because it churns the best in you for the benefit of mankind. So I think last night was a wonderful dinner. Some of you were part of the dinner last night, and perhaps someday you will also share a chair with such experts, hopefully. From quantum computing and secure communications to advanced materials, clean energy, artificial intelligence, and sustainable manufacturing, these technologies are redefining how societies function, economies grow, and nations compete. As educators and institutional leaders, we must ask ourselves a fundamental question. How do we prepare our students and research ecosystems for a future driven by such transformative science? At our group of institutions, our answer has always been clear: by fostering excellence in education, relevance in research, and responsibility towards society. At HITS and our group of institutions, we're completing almost 4 decades at our university and almost 6 decades our group of institution. Our founder started it way back in '66. We'll be celebrating yet another milestone very soon. We have consistently evolved to meet the changing demands of science, technology, and industry. Our collaborations with KCG College of Technology for this conference reflects our belief that institutional partnerships strengthen innovation ecosystems. Together, we aim to create platforms where ideas flow freely across disciplines, institutions, and national boundaries. The conference has been thoughtfully designed to encourage cross-pollination of ideas. The inaugural session has many lectures, panel discussions on quantum materials and intelligent technologies. The interactions and technical sessions bring together physicists, chemists, natural material scientists, computer scientists, engineers, and industry practitioners. This convergence is essential because today's breakthroughs rarely occur in isolation. They emerge as the intersection of disciplines. Equally important is the role of industry and innovation hubs represented here today. Intelligent technologies must move beyond labs into scalable, affordable, and sustainable solutions. Industry-academia collaboration is no longer optional, it is essential for national progress. Platforms like Quantum Horizons help align research priorities with societal needs, industrial capabilities, and global sustainability goals. Sustainability, in fact, must remain at the heart of all technological advancement. As we pursue quantum and intelligent technologies, we must ensure that they contribute to clean energy transitions, resource efficiency, climate resilience, and inclusive growth. From an institutional perspective, we view conferences like this not merely as academic events, but as strategic investments in the future. They help build global networks, attract talent, inspire innovation, and reinforce India's position in advanced science and technology. I firmly believe that India has the intellectual capacity, youthful energy, and entrepreneurial spirit to emerge as a global leader in quantum and intelligent technologies, provided we continue to invest in education, research, infrastructure, and international collaborations. I would like to take this opportunity to acknowledge the tireless efforts of the conference chair, organizing committee conveners, coordinators, faculty members, and the volunteers across the faculty members and the students from both the institutions who are organizing the event. The dedication and teamwork have made this prestigious conference a reality. Also thank our sponsors, advisory committee members, and international partners for their valuable support. As we commence this conference, I urge all participants to engage openly, question boldly, collaborate generously, and think beyond conventional boundaries. Let the discussions over the next 2 days plant the seeds of new ideas, partnerships, and innovations that extend far beyond this auditorium. In conclusion, I am confident that Quantum Horizons 25 will not only enrich our scientific understanding, but also strengthen our collective commitment to building a knowledge-driven, technologically advanced, and sustainable future. I would also like to mention my recognized Dr. Ajayan, who was kind enough to invite me and our academic, some of our researchers, to his wonderful University of Newcastle and Sydney last year for the 5th International Conference on Emerging Advanced Nanomaterials at Newcastle, University of Newcastle. Wonderful event attended by Nobel laureates. That's where I met Professor Bawendi, and his talk on nanomaterials was excellent. The conference lasted for 5 days, morning to evening sessions. It was very technical, so I could only spend 1 day, beyond which would not be possible for me to understand. However, the lectures were wonderful. There were professors from all over the world. And the wonderful point I'd like to mention, as a leading researcher in nanomaterials, he has one of the best centers in Australia. I hope some of you, he has given wonderful opportunities for our staff and students to get trained there. If you do get an opportunity, please make sure you don't miss it. He's a great professor and a leader. I think all of you must look upon to him and appreciate his quality of knowing each and everyone's name in that wonderful conference. He would call them all out, each of the speakers by name and designation, and that's how much he values the social capital which he has developed over the years. And that's what brings the best research resources to him anytime, all the time. And I must thank him for bringing a wonderful guest to our campus today, so all of us may experience and learn from him, and of course Dr. Ajay and all the other delegates who have come from across India and other countries. So I wish you all the best once again, and thank you all for being a part of this wonderful event. And I look forward to also the panel discussion which will follow this. We have a lot of children from across various schools. who have eagerly signed up, and they have some questions they would like to ask the panel. I hope the panel will be able to satisfy the scientific thirst and hunger of our youngsters of our country. Thank you.
Good morning to everyone present here today. I would like to also share that our Chancellor, Dr. Verghese, though unable to join us this morning due to prior commitments, sends his warm greetings and best wishes for the success of Quantum Horizons 2025 and to everyone gathered here today. It is a rare privilege in the life of any institution to welcome someone whose work has not only shaped a field of science, but has reshaped how humanity understands the invisible world around us. Today is one such moment. I have the honor of introducing our chief guest, Nobel Laureate Dr. Moungi G. Bawendi, Professor of Chemistry at the Massachusetts Institute of Technology. Dr. Bawendi did not simply study quantum dots. He redefined them. At a time when the field was unpredictable, unstable, and scientifically daunting, he chose not to step back. Instead, through clarity, patience, and visionary thinking, he transformed quantum dots from scientific curiosities into one of the most impactful materials of our era, now used in advanced displays, medical diagnostics, bioimaging, and emerging clean energy technologies. After receiving the Nobel Prize, Dr. Bawendi shared a profound thought. Great science happens when people feel free. Free to think, free to fail, and free to explore. That philosophy resonates deeply with the spirit we want to cultivate here at Hindustan. A culture where curiosity is encouraged, where experimentation is celebrated, and where young minds dare to challenge the status quo. Across 3 decades at MIT, Dr. Bawendi has nurtured hundreds of scientists, not merely to achieve academic excellence, but to become innovators who positively shape society. Many of his mentees now lead influential research laboratories, build pioneering companies, and push the frontiers of sustainability, medicine, and technology. As we gather here to explore quantum horizons, new materials, intelligent technologies, and sustainable futures, Dr. Bawendi stands as a powerful reminder that the future is built by those who push beyond what is known and imagine what is possible. Ladies and gentlemen, it is with immense respect and pride that I welcome our chief guest, Nobel Laureate Dr. Moungi G. Bawendi.
Thank you.
So I was born in Paris, in France, and my mother is French, there is Tunisian. And so Tunisia is a small country in North Africa, right at the tip of between Algeria and Libya. And so as a result, as a child, my parents moved back and forth between Europe and North Africa. And I was exposed to these 2 different cultures, back and forth. But as a child, I never really felt like I belonged in either one of those. And I was always a little lost. Luckily in Tunis, people spoke French, so I didn't have to struggle with 2 different languages, at least then. And here's me as a 6-year-old on one of my journeys back and forth between Paris and Tunis with my parents and my sister. And then when I was in 1971, when I was 10 years old, my parents decided to move to the US. And me as a 10-year-old child, in the airport in Orly in Paris on my way to become an American. My mother had tried to get me to learn English, and I didn't believe her when she said that people didn't speak French in the US, because they spoke French in Tunisia, right? And it was a different country. I hadn't needed to learn Arabic. And so when I got to West Lafayette, Indiana, in the middle of the US, I was a bit lost. The first child to come across the street to play with me started speaking to me in English, and I had no idea what he was saying. And I realized quickly that French wasn't going to get me anywhere in the US. Luckily, as a 10-year-old, you learn to speak languages quickly, and by 6 months later, I was fluent in English. But this being lost, started from this very early age, going between continents, and it continued. And in fact, when we moved to West Lafayette, Indiana, the university that is there is called Purdue University, P-U-R-D-U-E. If you replace the first U in that word, it spells P-E-R-D-U-E, and if you know French, that spells perdu, which translates to lost. So it was a perfect place for me to arrive to there. So from West Lafayette, we moved back to Paris again, so we kept going back and forth. Eventually, I ended up in Harvard University and went to college there. And again, Harvard University was on the east coast of the US at the time in 1978. It was still populated largely by private school students from the east coast, largely, a little bit from the west coast, but very few from the Midwest, and I was a little bit I was lost, and let's just say. I was so lost that when I took my first chemistry exam in late October of 1978, I promptly failed it completely. I got the lowest grade in the class. It was a 21 out of 100, and that was generous because I looked at all the questions and I was paralyzed, and I just wrote a little bit on each question, and all the partial credit, I ended up to 21, but really it should have been 0. And so that was my first big failure on my way to becoming a scientist. And science is really a series of failures, because you have some ideas, you try them out, they don't work, you overcome these challenges, and then you make things work, and then you proceed step by step like that. If you know the answer when you're doing research, then what are you doing? You already know the answer. So research is about finding new things, and when you find new things, usually you don't get it quite right at the beginning. So, or having to overcome that first failure was just the normal process of doing science. I learned to study, and then I didn't fail anymore. I learned to overcome that first failure. After Harvard University, I went to the University of Chicago to do my graduate work, and I loved mathematics, and I started out as a theorist. I was doing polymer theory, pen and paper theory, not computation, and it was great. I learned a lot, but during the first 3 years, those first 3 years when I was doing theory, I realized that I was missing something. I was missing the exploration of an experimentalist, of looking to see how the world works and discovering that part and understanding it. My brain wasn't wired quite enough as a theorist and being an experimentalist, so I switched. I switched to do experiments, and that led me to doing work on very small molecules, ions, charged molecules that are of interest in the interstellar space. It turns out that space is full of molecules, small molecules that are bombarded with cosmic rays that get charged and that react with each other. For example, the molecule that I spent a lot of time on as a graduate student was the smallest polyatomic molecule you can imagine. 3 protons and 2 electrons, that's H3+. Hydrogen is one of the most one of the most abundant element in the universe. And the atmosphere of the big planets like Jupiter is largely hydrogen, so it's extremely common. And H3+ is made to transport protons from one molecule to another molecule. So it's a very reactive species that's really important in interstellar chemistry. So that was wonderful. I really enjoyed working on there, and I got to learn and really understand quantum mechanics, because when you're dealing with a small molecule like that, that's very floppy, everything has to do with the motion of the atoms in that molecule is very complicated, as it turns out, and was completely described by quantum mechanics. So that was really, I loved it, but I really loved that field of small molecule spectroscopy and understanding their motion was a field that was actually pretty old, because it dated from the dawn of quantum mechanics in the 1920s, and there was a large community. And from my experience as a child and then as a student, as you remember, I didn't feel like I fit in any community. And so suddenly I had to be part of a big community, and it didn't feel very comfortable. It wasn't very comfortable to me. And I wanted to do something where I was a little bit more isolated, let's say. And then I went to Bell Labs, and I had the privilege and the luck of working with Lou Bruce, who had discovered the effect of quantum confinement and quantum dots a few years earlier. And that's why I went in his group for a summer. And then I did condensed matter physics, quantum physics at the solid state level. And I just fell in love with it. And also Bell Labs introduced me to the connection between science and technology, because Bell Labs had so much technology involved there, and so many inventions that we rely on today, like the transistor, the optical fiber, and the photovoltaic cell, for instance, etc. So at Bell Labs, I was exposed to this new idea of quantum dots, this new idea of nanomaterials. We didn't call them nanomaterials then, because that word really hadn't entered the lexicon, because this was just at the very beginning of being able to manipulate matter at the atomic scale to create materials that have nano size where you can engineer their properties. And so this brand new field, and for me that was perfect, because nobody else was working on this, or very, very few people. And so every question that we asked was a new question, and every answer was a new answer that engendered another question. And so this was really a wonderful place for me, because I didn't have to worry about fitting into a community, because there wasn't a community to fit in. And so when it came time for me to go back to do a postdoc, I went back to Bell Labs. After Bell Labs, I started at MIT using the knowledge that I had gained at Bell Labs to start my own group on quantum dots. Now let me tell you, when I was at Bell Labs as a postdoc, the quality of the material that was being made was not very good, because it had just been discovered. And when I was at Bell Labs, I stumbled across a way to make the material a little bit better. But it only worked every now and then, and I could only make one size of these particles. And when I got to MIT, I tried to reproduce what I had done at Bell Labs, and it didn't work. The magic of Bell Labs stopped working at MIT. And that forced me, that failure of reproducing these early results at Bell Labs, forced me and my students to rediscover the material, rediscover how to make the material. And I'm going to tell you a little bit about that. But before I do that, let me go and explain what is a quantum dot. A quantum dot is a small particle, a nanoparticle of a semiconductor. Here I have it as a binary semiconductor that has two elements, for instance, cadmium and selenium, or gallium and arsenic, or indium and phosphorus. And it's a particle that has a few thousand atoms, maybe. It's 2 to 20, 30, 40 nanometers in size. How do you know that you've made it? Well, you know you made it by using a tool that had been invented not so long before the 1980s, when this was discovered, which is the electron microscope. So many discoveries, or I would say most discoveries in science, are built on top of tools that allow us to probe them, right? In this case, the electron microscope is this really important tool that has allowed nanoscience to explode. Without these tools, we would be completely blind, right? Just like the light microscope has allowed biology to explore cells and really learn a lot about the world on the micron scale, the electron microscope is this really crucial tool that allows us to see the world on the nanoscale. It's one of my students with an early electron microscope there. So when you have a sample that looks reasonably good, then you use the electron microscope and you can see a series of particles that look about the same, and you know the quality is homogeneous, they're all about the same size, you can see that they're roughly spherical, etc. Okay, so that's the nanoparticle part. But what about the quantum part? So the quantum part has to do with quantum mechanics. Quantum mechanics describes the world at the microscopic level, at the nano level, the sub-nano level. And quantum mechanics is this wonderful, magical description of the world that's completely counterintuitive. And you just have to believe that's the way the world is because it works. It works to describe it. And one of the fundamental tenets of quantum mechanics is that the particle wave duality of matter. That particles, when you look at them at the microscopic scale, for instance, an electron in an atom or in a molecule, don't necessarily behave like little particles flying around a circuit. So if you think classically, you think of an electron in a wire or an electron in a circuit, like in your computer, you think of it as a particle that moves back and forth, carrying charge and bringing information. But if you take that particle and then you stuff it in a little box, a little nano box, then that description of the particle moving quickly stops being correct. The particle now behaves like a wave. The electron behaves like a wave. It fills the entire box, just like in a molecule, like in a hydrogen molecule. These electrons are in the bond, and they don't go back and forth between the two protons. They're just there, gluing the protons together like this wave. And so, because these electrons are now behaving like waves inside a nanobox, and our nanobox is our little particles that of the waves become dominant, right? And one of the properties of the waves know, for instance, in music, sound waves, is that when you put a wave in a cavity, and in a wave, this quantum dots or these nanoboxes are spherical cavities. They confine that wave to be inside the sphere. So when you take a sound wave and you put it in a cavity, the pitch of the sound reflects the cavity size, right? So if I have a flute and a piccolo, flute is bigger than a piccolo, and so the pitch of the flute is lower than that of the piccolo. It just has to do with the sound wave and the cavity size. Just like for organ pipes. If you have a bunch of organ pipes, you have small ones and big ones, and the small organ pipes that I've color-coded blue here have a pitch which is higher than the medium size, which are color-coded green, or the big ones, which are color-coded red. And so pitch then for sound waves reflects the size of the cavity. The same thing happens for an electron in a nanobox, right? It's in a little spherical cavity. It's not macroscopic like an organ pipe, it's microscopic. We have to use the electron microscope to see it. But for the electron, the idea of pitch is energy. So for a small cavity, the electron has a higher energy than for a big cavity, just like for sound waves. So now we have a bunch of cavities that we can make synthetically using chemistry, if we know what we're doing. Then we need to put an electron in there, right? We need to put an electron there and see how it behaves. How do you put an electron, one electron in there to create that wave? Well, there are a lot of electrons in there already because it's full of atoms. There are thousands and thousands and thousands of electrons in here. But those electrons are all lined up right next to elements like titanium or indium or whatever, and they're not free to explore the entire boxes away. So we've got a single electron in there, and these things are too small to put wires. So how do you do that? The way you do that is you shine light. You take some, let's say blue light, this is one of the ways of doing it, for instance. You take blue light, and then the energy of the blue light then releases one of the electrons from next to an atom and releases and allows it, liberates it, and allows it to explore the entire box. Okay? Eventually, that electron that's been liberated goes back and finds where it came from and releases its energy, that's its wave energy, and you see that as light, as a photon. So this is a way then of taking blue light, creating an electron wave whose energy is determined by the size of this nanocavity, and then eventually that wave in the nanocavity gets released as a photon of light of a different color than what you started out with. And so if you have a bunch of samples of quantum dots in solutions, as we have here, you shine UV light or blue light on them, then you see different colors coming out, and those different colors then reflect the size of the cavity and the effect of that electron that you've created in there in those cavities. That's really all you need to know about quantum dots, really, to begin to understand the physics of them. They're much more complicated than that, you know, because there's a bunch of atoms in there, and the physics are really wonderful. But at the very fundamental level, this is really all you need to know about them. And in fact, for the simple applications, this is also really all you need to know about them. Okay, so the Nobel Prize, what was it about? Well, it was about not just about quantum dots, it was about also nanoscience, because this was the beginning of nanoscience. This was the beginning of being able to manipulate matter at that size scale and to change its properties as a function of the number of atoms. Engineering material at that size scale and having quantum mechanics dictate how those properties are going to change. Some materials are going to change, like semiconductors. I mean, if you took an oxide, like a little piece of glass, and made it smaller and smaller, you wouldn't see these effects. So these quantum effects depend on the material that you choose. Here I'm joining Louis Bruce and Alexei Ekimov the day of the award, and December 10, 2023. We're all wearing the same outfit, the same costume. These are white tie tuxedos, and all the men at the award ceremony and also in the banquet afterwards, and this is a huge banquet, there's like 1,500 people in the banquet, all the men have to wear exactly the same outfit. The women can wear gowns, you know, as long as they go to the floor, but the men all have to wear exactly the same thing. One shop in Stockholm that makes this, all their money, you know, the week of the Nobel Prize, and you return your costume. Okay, so Louis and Alexei were awarded the prize for the discovery of the quantum effect, and I was awarded for the synthesis. Both Louis and Alexei, as well as I, were driven curiosity to figure out how the world works. Alexei Ekimov was interested in what gave the to stained glass windows. So it was known already, Faraday knew this back in the 18th century, that if you take gold and break it up into little tiny pieces, it doesn't look yellow anymore, it's red. And if you put that into glass, then you have red glass, red tinted glass, which is what you use for stained glass windows. What about the other colors? This is the question that Alexei was interested in. So he took glass, put different elements in there, and started processing under different conditions. And he found that with the exact same number of elements in there, depending on how he processed it, he got different optical properties, different colors. And he used small angle X-ray, which allowed him to look at the size of the particles, the little crystals that he was creating in the glass. He was able then to correlate the size of the crystals that were forming with the color that he was seeing. And he realized that this was a quantum effect. And he wrote a paper in 1981 with the first 3 words, quantum size effect, to describe what he had observed. Bruce was also working, so Alexei was working in the Soviet Union at the time, and separated from the Western literature. Bruce was working in the US at Bell Labs in New Jersey, and he was also driven by curiosity. He was driven by curiosity on how fast an electron can go from inside a semiconductor to a solution that has molecules in there that can do photochemistry, that can do electrochemistry. This was during the OPEC embargo of the 1970s. There was an energy crisis, and people were interested in learning how to make fuel from the sun, something we're still interested in doing. And there was a tool that was invented in the 1970s. It was called the picosecond laser. Really a laser with short pulses. Today we have lasers with much shorter pulses. Picosecond lasers and nanosecond lasers. Picosecond laser was this amazing invention. And it was fast enough, the pulses were short enough to be able to resolve the kinetics, how fast an electron would go from inside a semiconductor through the interface into a solution. And so Lou Bruce was interested in using this new tool to figure out, to understand this quantum process really of transfer an electron from inside a material to the outside of the material. He was making these semiconductor particles because you want to maximize surface to volume ratio because it's an interface process to get the biggest signal to noise. And he found that whenever he made a new sample, the colors seemed to be different. He was using cadmium sulfide at the time. And he thought maybe he was doing something wrong in the lab, making the material. But he had a tool available to him, which was the electron microscope. Bell Labs was wealthy enough as an institution and had good electron microscopes. And he found that the color that he was seeing wasn't because he was a bad experimentalist, but it was because the size of the particles in the microscope correlated to the color that he was seeing with his eyes and also with the tools to measure the color. And he understood the effect as a quantum effect and wrote a paper in 1983 with the first 3 words, quantum size effect. And Alexei and Lewis didn't know each other, they didn't know their own words. Science was ready for this discovery. It happened independently. It wasn't until many years later, after the fall of the Berlin Wall, that Lewis and Alexei met each other and started to communicate with each other. Where do I end? Well, the talk is also about patience in science and patience in science becoming a technology. So from 1981, 1983, etc., the beginning of the discovery of the quantum effect, then Lewis at Bell Labs started to think about how do I make my samples better? Because they weren't really good. They were good enough to see this effect, but if you looked at the particles in the electron microscope, you didn't see at all the little beautiful particles that I showed in the beginning of my talk. In fact, you saw particles of completely different sizes, they were very inhomogeneous, the shapes were completely misformed, and they were full of defects. So they were good enough to see this effect, to discover the effect, but not nearly good enough to be able to understand the physics of the material, to really probe the quantum mechanics of the material, and to be able to make a technology out of it. And when I came in as a postdoc, that's where I discovered a potential path towards making better materials, and which had to do with taking the stuff that Lewis and his colleagues were making and heating it up a little bit to make the crystal a little bit better, using certain molecules in the solvent. And as I mentioned, this discovery that I made, which was really an accidental discovery at Bell Labs, only happened every now and then. And I used a very technical term to describe my discovery back then, and the technical term is magic, because I couldn't understand it, and it only happened every now and then. And I had that on my slides when I described, this thing to the management at Bell Labs. When I moved to MIT, I promised that I would follow a different curiosity, which was to figure out how properties of matter change when you go from the atomic scale to the bulk scale. If you take an atom of silicon, its properties are completely different than a bulk piece of silicon, like what you have in your computer. So how many atoms of silicon does it take for the properties of a computer chip to start, right? Do you need 5 atoms, 10 atoms, 1,000 atoms? So that's the kind of question that I was curious about. The progression of the properties as a function of the number of atoms until you get to the bulk material. And so I came to MIT and I tried to reproduce the magic of Bell Labs, and it didn't work. And that's where I had to rediscover how to make particles, and wrote a paper in 1993, essentially 10 years after the discovery of the quantum size effect, with my first 3 students, and this is the part of the synthesis of the Nobel Prize. So let me tell you about this process to make these well-defined nanomaterials that we engineer. And it's a very simple process. Many things, it's simple in intellectually, but the complexity is in the details, right? It's a simple process, but you have to get it right. You have to get it right. You have to get it right to have all the conditions to get it to work. So what I had realized after my time at Bell Labs was that in order to get these materials to really perform well, to really begin to understand them, we needed to put a high temperature because we needed to make crystals. And crystals are, the elements need to be able to find where they go. And the higher the temperature, the easier it is for them to go there. We were limited in temperature because we're doing chemistry here, so the higher temperatures that we're talking about is like 350 to 400 Celsius. The second thing we needed to get rid of oxygen and water. Because these semiconductors, the surface is reactive to oxygen. It turns to an oxide. It's like if you take a little piece of iron, a little tiny grain of iron, and you put it out in the rain, it doesn't stay as iron, it becomes iron oxide or rust. The same thing happens with these semiconductors. So we needed to get rid of the water and the oxygen completely and make everything out of nitrogen. The third thing was that we needed to separate the nucleation and the growth of the crystals. That was a concept that was known already since the 1950s, but for making bigger crystals, microscopic crystals that are on the micron or millimeter size scale. That if you have little seeds of crystals, and then you grow, if you have the seeds are roughly all the same size, and grow on top of the seeds, then the growth becomes uniform, and you end up crystals that kind of all look like each other. And so we needed to implement those three ideas. And this is how we came out with this, what is now called the hot injection method. We have metal organic precursors that are stable at room temperature, that contain the elements that we need to grow the crystals. We quickly inject them into a hot solution that contains, here we call them ligands. They're organic molecules that bind to the surface to prevent the crystals from growing too quickly. When they hit the hot solvent, these metal organic precursors decompose and release the elements, the metal elements, like the cadmium or the selenium, and those begin to nucleate quickly. So that's the one-step nucleation. When the concentration drops because you've nucleated a bunch of seeds, then you have growth follows, and this growth can be slow. And then you can watch the process, and when you're done growing, you just turn the heat off, and it's like baking. Take your cake out of the oven, and then it's done. It's done. Okay, and then and this is how it looks like. So this is a YouTube video that was from 2010, I think. It's still the same process. So there's the hot solution at 350 Celsius. You can see the team rising up the condenser there. At quick injection gave 2 nanometer or so particles, and that was the orangish, reddish color that you saw. And now we're going to wait a little bit, like 20 minutes, but you don't have to wait. The video sort of skips 20 minutes. Now it's much darker color because the particles are bigger. You follow the slow growth. The student is taking out aliquots, and you see the color change as a function of time. That's the growth of the particles, the uniform growth of the particles. And then my student there is going to use a UV lamp to liberate that one electron in the particle. So these are solutions of these nanoparticles. And you see the light coming out reflecting the cavity of size for that one electron that sits inside these quantum dots. Okay, so then we wrote a paper in 1993. This was my first paper as an assistant professor. So I started in July 1990. I spent 6 months failing over and over and over again trying to reproduce the Bell Labs results. And it wasn't until 91, 92 that we had material that was good enough that we could feel confident that we could start to learn something about the quantum size effect, the quantum physics of these small objects. We wrote the paper in 1993. Today, when I have colleagues that don't write anything as a professor for 3 years, my colleagues think that there's something wrong with them. They think they're going to fail miserably. And I did have pressure to write a paper when I was starting out before writing this paper. In fact, one of my students really wanted to publish before we were ready. And I told him the world doesn't need another way to make bad particles. You know, we needed to be. I was a little bit of a perfectionist, and you know, I guess in the end it paid off. So there was a few words that are important. The fact that it was simple. You know, conceptually, it's a simple process, a single reaction. Those words turned out to be important to make it a technology, to commercialize it, because anything that you make, the cost of making it depends on the number of steps. The more steps you need, the more expensive it is. It doesn't matter what it is. You know, the complicated molecule that you use for a therapeutic, let's say for oncology, the more complicated the molecule, the more steps you need, the more expensive it is to make. Not necessarily to sell or to buy, but you know, the cost of making it. The steps you need, the it is to make, the more expensive it is to make. Same thing with this. So the fact that it was a single step has out to be really important. Today, these materials are made in huge quantities. They're not made in little flasks, you know, with 100 milliliters or so. They're made in 3,000 or 5,000 liter steel containers. Huge, huge quantities. And they're made every day in 2 factories, one in Japan and one in Korea. When we first thought about licensing these things back in the late 1990s, this was going to be completely impractical. Because if you looked at the cost of the little bottles that we used to, you know, to do it on the lab scale, the cost would come out to about $10,000 to $20,000 a gram. Completely impractical, they said. But what I knew already intuitively was that, yeah, that's true if you do it on the lab scale. But if you scale things up, then costs really start to plummet. And today, the cost probably is, they can probably be made at $1 a gram. Just because of the scaling of the process. Beginning, all the costs were labor costs. Today, it's completely automated. Reagents come in on one door, you press a button, and quantum dots come in go on the other side and get loaded into a truck. The other thing that's underlined here is something that's called size selective precipitation. A fancy description of a purification process. Whenever you make a new molecule, you want to purify it. You want to make it so that it's the only thing you have. We know how to do that with molecules in chemistry, but we didn't know how to do that with these nanomaterials. So we had to invent a way to purify our nanomaterial so that it was the only thing that was in our bottle so that we could use it and understand it. Okay, so I'm going to show just a little bit of data here. What you see here is an absorption spectrum that has 3 defined transitions. The lowest one, the reddest one at 550 nanometers, and that's the fundamental. That's that sound wave, you know, that's the fundamental wave from your flute or your guitar. And the slightly, the ones that are to your left there, those are the harmonics. So for the first, we were able to see harmonics in our cavity. And the other thing that we were able to see was this fluorescence, the thing that's labeled fluorescence, that's the color of the light that's coming out. And in this paper, you know, we said that the efficiency of getting light out was around 15 to 20%. And to me, that was amazing. That was so bright. That was so efficient. Because before it was 0%. And 15% is infinitely bigger than 0%. I was so excited. And then one of my colleagues in Germany said, about 15% means that 85% of your sample is worthless. And he was right. And so that really pushed us to make that number of efficiency even higher. Today, the efficiency is about 100%. We showed in that paper what the exquisite control that one can have at the nanoscale in terms of affecting the properties of the material. So you see a series of spectra there, you know, one on top of the other there, slowly marching across the visible from 400 nanometers to 700 nanometers. The difference in size between any one of these curved spectra is no more than a couple handfuls of atoms. And these are taken, you know, you let the thing grow, you take some samples out, you take the spectrum, And that shows the control that one can have with a very simple process at the nanoscale. You know, if you have everything going right, you can really control things well, and that control then allows you to see the quantum effects change as a function of size in this case here, and then harness those quantum effects. A big advance in the field came a little bit later, so let's go to the timeline. The discovery was around 1980, let's say. The synthesis was about 13 years later, 10 to 13 years later. Things begin to accelerate. Once you have a material which is reproducible, which is characterized, which you can purify, which is of good enough quality to really begin to understand it and use it, then the rest of the world begins to notice. And what was before just a handful of people working in the entire world on the material suddenly became a lot of people. A community began to form. A community of nanoscientists, in this case here, quantum dot community. And that community, which when I was part of this, figured out we could make these things more robust and increase the efficiency of the color by encapsulating the quantum dots in another solid material, these core shells. So the core is the quantum dot, and then it's surrounded by a bunch of shells. It's like M&Ms. You know, the M&Ms melt in your mouth, not in your hand. So the soft chocolate in the M&M is that quantum dot, and the hard chocolate on the outside is the stuff that prevents it from melting in your hand, right? And so these core shells were super important. So once you have the core materials and the efficient emission, then you can start talking about applications. You know, we did a lot of understanding of the physics with it as well, which I'm not going to get into, but the applications started to come quickly then. So 96, 97 was the core shell idea, just 3 years after the synthesis. And the first company to commercialize an application was in 98, just a couple years after the core shell discovery. And that was in biology. It wasn't in biology because we were chemists. And biology is the closest thing to chemistry, right? And so we knew that, as a community, we knew that the biologists were using dye molecules to image cells, to tag cells, to watch the different parts of cells. And so we thought, well, quantum dots, because they're the same size as a big protein, we should be able to use those to tag cells as well. And they should work better than dye molecules because they're little pieces of rock. And so they should not get destroyed by light the way that dye molecules are. And so if you look at this series of photographs here, this is the nucleus of the cell dyed in red, and the cytoskeleton is dyed with green dyes. The red are quantum dots, and the green are dye molecules. And you watch, as a function, you illuminate the cell, the green color goes away. That's called photobleaching. This dye molecule is degrading. But the dots don't degrade, they just last and last. This material showed that it was quite robust. We could do some complicated experiments, not with just with dead cells, but we could do it in vivo, in animal models. So this is a cartoon of showing how we can find rare cells, in this case here cells like stem cells, that overexpress a couple receptors on their surface that are not expressed by other normal cells. So we can come in with two colored dots, red and green emitting quantum dots, and then look for yellow, because red and green together make yellow, and then you look in your microscope, you find a yellow-looking cell, you know you found that very special cell, and it starts to study its environment, and we did this with collaborators at Harvard Medical School. These are hard experiments. They teach you about science, they teach you about biology, they teach you about cancer, they teach you about all sorts of really interesting things. But the big application, at least financially big application, didn't come until we started to think about talking to electrical engineers. Okay, started talking with electrical engineers. There was, at the beginning I said, discoveries are built on tools or other discoveries. In this case here, the discovery of the gallium nitride diode, the blue emitting diode from the 1990s by Chia Corporation, which also was a Nobel Prize, was instrumental. So these gallium nitride diodes have changed the efficiency of lighting in the entire world. Well, we use gallium nitride diodes everywhere. They're used to power our displays. They've really changed the way that we make light. but they emit light in the blue at 465 nanometers. Well, it turns out that our quantum dots, all the sizes, can all absorb blue light. So the green spectrum here is the absorption spectrum. There's a big absorption at 465 nanometers, and all the colors are the same. They absorb very strongly there. So we could have blue light and a shine dot on dots. These are dots that are embedded in polymer, and they all shine different colors, but they're all being excited by this blue light here. It's a very simple idea. You take blue light as your engine, then you can create any color you want. Okay? Very simple idea, but I mean, there's a lot of chemistry to go from that idea to implementation. Two companies were formed out of that idea, Nanosys, two startups, Nanosys and 3D Vision. My students had something to do with both of them. Neither of these companies exist today, really. Nanosys is part of Shoei. Shoei is a Japanese company that makes quantum dots in huge quantities for the display industry. 3D Vision is now part of Samsung. So Shoei makes all the quantum dots for companies that are not Samsung, and Samsung makes it for themselves. And the first product that came out with this idea of shifting color using gallium nitride diode and quantum dots was a light bulb. So this was 2010, not so long ago, when these LED light bulbs first came out. And these LED light bulbs were too blue. There wasn't enough red in them. There was a blue gallium nitride diode coated with a phosphor, a yellow phosphor. There was a lot of blue, a lot of green, a lot of yellow, but no red. And so you looked at yourself in the mirror with these light bulbs. You know, let's say you woke up in the morning and brushing your teeth, you look at yourself in the mirror and you think that, you know, something is wrong with you. Because there's not enough red, right? And so you think you're sick or something, you go back to bed. And so the trick is to put back some of that red. And one of the ways to do that is to put dots to absorb some of the blue and turn it into red. Simple idea. So this was an example of a light bulb that was sold by Nexus. You could buy it on bulbs.com. And that was a great technology, and it worked well. But financially, it turned out to be really hard because it worked fine when the light bulb cost $100 a piece, and you could add an element of an optical element to those and make some money. But when the light bulbs started to cost $5 a piece, then there wasn't enough margin to add anything to that, right? So what we really want to do is you want to put the dots right on top of the diode, but there's some technical challenges to that because the diode gets hot, there's a lot of flux, light flux. Those challenges are being solved today, but they're not there yet. Anyways, these light bulbs still exist in my office just fine. They were just too expensive today, right? So our product no longer exists. The same idea. So 3D Vision and Nanosys both arrived at the same solution to an actual problem, which was to pivot to a different application. That application was displays. And so think of using then a blue diode for the display. Instead of coating it with a phosphor to make white light, and then wasting a lot of the colors or filters, the blue diodes, and then you take some polymer that has the dots in there. They absorb some of the blue light. You have red emitting and blue and green emitting quantum dots in your polymer. Now you have RGB in your backplane. You have the three colors that you need to make every color that the eye can see, because we have three kinds of rods in the back of our eye. And so that implementation was first put on the market by Sony in 2013 with quantum dots made by 3D Vision. It only lasted for one model year and only a few TVs. And the reason for that is that even though you can demonstrate something in the lab at small scale, like 3D Vision did, to convince Sony to make their TVs, 3D Vision promised Sony that they would scale up the process, going from handmade tubes of polymers to millions of tubes of polymer within 6 months. That turned out to be really hard. Scaling up turns out to be hard. It's a different kind of engineering than the discovery process and the first proof of concept things. And they weren't able to do it. Samsung, on the other hand, So so I have a couple of these TVs. They were great. They're over-engineered, but they're great TVs. Samsung, on the other hand, saw that and realized this is a great idea. This is a great idea, and we're going to spend money and time on this. And they bought QD Vision, but really what they bought was the logo, QLED. Because if you look at that logo QLED, there's a little bar on that first circle. You remove that bar, and it says OLED, right? And who was selling OLED TVs? LG. Now Samsung could say, oh, we're better than LG. We've got something that's better. You know, it's QLED, it's quantum instead of organic. So that little bar, you know, was probably worth tens of millions of dollars when QD Vision was sold to Samsung. But in any case, QLED TVs are now the bread and butter of Samsung. They replaced the cadmium with indium for toxicity reasons. And today, the QLED TVs, the quantum dot enhanced TVs from Samsung, are OLED pixelated TVs, but they use blue OLED, so that's the blue color, and then they inkjet print on top of that quantum dots of the two different colors that make green and red. And they have these QD OLED TVs that are these beautiful, they can make them much brighter, it's much easier to make, it's cheaper to make, etc. So in fact, Apple's new MacBook is going to have a QD OLED display as part of it. It's really caught on, and every single display maker talks about having quantum dots in their displays today. Okay, but so that's the financial success, at least for the companies, not for me, but for the companies. Applications. You can use the same idea of downshifting using these quantum effects to catch sun, you know, and then you replace the color of the sunlight that comes out, you replace it with, let's say, red light or some other red light. It turns out to be interesting in agriculture. If you can make the dots cheap enough, and you can make a film of polymer that has the dots inside, and you can cover a greenhouse, take some of the blue light from the sun, make it into red light, and it turns out that some plants, like tomatoes and other fruits, give you better yield if you decrease the blue amount of blue and increase the amount of red light. So there's a small company that I actually don't have anything to do with that's commercializing that. You can use quantum dots as part of photovoltaic cells to increase the efficiency. There's all sorts of applications in that range as well. So, you know, the future is going to be electroluminescence, flexible displays using quantum dots, photovoltaics to harvest energy, and also it turns out that we can use the quantum dots as part of sensors to detect light of all colors, including the infrared. And there are small companies that are trying to commercialize that as well. So where are we today? Where did we come from? So we came from this curiosity back in the 1970s, late 1970s, for me the curiosity about how matter gets its properties from the initial atomic properties in the early 1990s. Then once we had a material that we could study, a lot of physics came out of it. We understood a lot of the quantum properties of the material. And then when you have a new material, and you ask the question, what is it good for? What can I do with this? So that happened very quickly, right? So 10 years or 13 years of very little apparent progress, and then you have a material that you can handle. And then very quick, you know, as humans, we're very ingenious, and then we have something new, we can decide, let's use it for something, right? And so all these applications come out. The same process that we use for semiconductors is for metals, semi-metals, magnetic material, all sorts of materials. This idea of controlling material at the nanoscale so that it acquires new and interesting property. What we pioneered was really a process of figuring out how to make and characterize these sorts of materials. And we can make similar materials with all sorts of shapes, all sorts of core shells. We can combine them together. You can think of these materials as a new brick, where the different particles are different atoms. Then you combine them together into assemblies and get new properties out of that. So real applications in displays, all of in biomedical imaging and light sensing and solar energy, those are real applications where people have either put them at scale and commercialized or are attempting to do that. The new applications coming up are going to be in catalysis, in electronics, and optics, in quantum systems. That's my favorite application, quantum information, and using these particles for quantum information. I've had a lot of students where it's not an isolated science, as it turns out. In fact, unfortunately, perhaps at the beginning, it's really a social, it's a social adventure. And you can only do this if a lot of people work together on this. And if you multiply my 150 students or so that I've had with all the groups that are working on this, there are thousands and thousands of people throughout the world that are working on these materials now. This is just on quantum dots. Finally, as a Nobel laureate, you keep getting asked, what's your advice to young people? So I ended up writing these 5 bullets one day because I was asked to give a very general talk to students. And this is what I said. So you stay curious, because curiosity is what leads to discovery. Right? Curiosity is what leads to solving problems. You have a problem that in your experiment, you have to be curious about how your experiment works so you can solve the problem. You see something, you don't know how it works. You have to be curious to figure out, why does it work the way it works? How does it do that? So that's the most important part. The second one is to keep learning. Luke Bruce used to say, you should try to learn something new every day. Learn one thing new every day. I think it's super important because if you keep learning about different things, then you can combine things together. You can figure out how things are connected. You can take your discovery and apply it somewhere else. Be flexible, because science is a series of failures. You fail, you overcome the failure, and sometimes you have to change direction. You have to figure out, okay, this isn't going to work, I got to change direction. And so, be flexible, but don't give up, right? There's an answer out there. There's an answer to your path out there. It's not a dead end. It might not be where you think you're going, but there's a path that ends up somewhere. And along the way, if you're not enjoying what you're doing, then you're not doing the right thing. So enjoy life as well. Thank you.
Thank you, sir. It was truly a blessing and a privilege to listen to a Nobel laureate, and I'm sure everyone in the hall benefited from your address. Thank you so much, sir.
Ladies and gentlemen, and I'd like to thank the conference organizers and my good friend Dr. Ashok Vakis for inviting me to deliver the keynote address, the Quantum Horizons 2025 Materials, Intelligent Technologies and Sustainable Future at the Hindustan Institute of Technology. I think giving lecture after Nobel laureate lecture is always scary. He has taken you the world of quantum materials, and I don't have to repeat now what are quantum materials and their applications are. But I can present you something exciting that I learned from his 3 decades of research. He elegantly demonstrated us, all of us, that how by just simply tuning the size of the nanomaterial can unlock unique properties of this nanomaterial and lead new technologies, and that can change the life of so many people, from display technologies to drug delivery system to even sensing technologies, covering energy, environment and health. Today in my talk, I'm going to show you some of the materials and how we can change the properties of the material by simply changing the nature of the elements and structure, morphology, and even porosity of this material. For example, carbon. With the nanoporous structures, and it may be a partially conducting, but depending on the framework, it may be a conducting material. But if you change the framework from carbon to carbon nitride, it will become semiconducting material. But if it is a boron nitride, and it will become insulating material. So by changing the nature of the elements in the framework structure of the material, one can change the properties of this material. But not only that, it can change the surface, catalytic and sensing properties of the material, and that can dictate the performance of the material in various applications that is shown here. For example, carbon capture and conversion, clean energy generation, energy storage and conversion, and even the drug delivery system. Over the last 25 years, my team discovered a series of advanced nanostructures, including a nanoporous carbon nitride, nanoporous boron nitride, nanoporous boron carbon nitride, nanoporous fullerene, nanoporous biomolecule, and even various carbon-based nanostructures, and published quite a lot of papers in top quality journals. Also, we use a theoretical calculation to understand and predict the performance of the material, or to know more about this material. And once you know that, and we can apply them for various applications, including energy storage, carbon capture and conversion, and even the drug delivery. But these are all the fascinating material that you can see here. See, they have got a highly ordered structures and a unique morphology, with a fascinating conducting, semiconducting, and insulating characteristics. But preparing the material is not only enough, but he has beautifully demonstrated that how these materials can be available to make an impact to the world and to the society. That is the key. That is the key for the success, and that got him the Nobel Prize. And today I am going to show you the material that I have discovered in our lab have the potential to change the world, or to save the world, or to help the society. And how? I'm going to take you in a few minutes what the world is facing and what are the problems that we are facing. So one of the problems is this global warming. And from where it is coming from? The CO2 concentration in the atmosphere. 400,000 years ago, the CO2 level in the atmosphere is less than 250 ppm. It was going up and down till 1950. And after 1950, you see there is a huge rise in the CO2 emission. See, 400,000 years in the nature, Dr. Ashok was telling that nature has its own mechanism. Yes, of course. And it was just managing it till 1950. But after 1950, after the automatic revolution, right? We have been so greedy that we continue to use large quantity of the gasoline or coal kinds of energy that liberated huge quantity of the CO2 to the atmosphere. But in the current level is of 430 ppm, which is an alarming level. And why we are worried about the CO2? CO2 is a nasty molecule that has a tendency to absorb the heat that is reflecting back from the earth. And once it absorbs the heat, that heat will be reflecting back to the earth and warming up the earth. And you see the rise of the temperature all over the world, drought everywhere, killing hundreds of thousands of people, right? And from where it is generated? The fossil fuels, coals, oil, and so on. We have 8 billion people and we need 580 exajoules of energy. All energy is coming, most of the energy is coming from the fossil fuels, and that emits huge quantity of the CO2. And if you don't take it seriously, and this is going to be a disaster, because the population is going to be exploded, and it is going to be 10 billion or 11 billion dollars, 11 billion in 2100. Everybody needs energy, but in 2050 we need 750 exajoules of energy. In 2025 alone, we liberated more than 36 billion ton of CO2 to the atmosphere. And if it goes like that, it will be 40 billion tons of CO2. That is huge. Of course, nature has its own mechanism. That ocean, which is the basic in nature, CO2 is acidic in nature. It can take 70 to 80% of the CO2. And people can say that yes, it is huge. It can even take more. But ladies and gentlemen, but the issue is, when the ocean takes too much of CO2, it gets acidified. When it gets acidified, it affects the living organisms in the ocean. That's a huge issue. So the global warming and affecting the living organisms in the ocean. Right? So that's why now the researchers and politicians are jumping into finding a solution. Okay, can we increase the efficiency of the energy to solve the problem? Or develop a renewable energy expansion? Or use some innovative strategy to find a new form of energy technology that Professor Bawendi was mentioning. It's not only single technology, but there are so many low energy technology that people can use it. Or public awareness or the policy development. Because this is quite crucial. Because we have to tell our kids, when you go out of the house, you turn off the light. If you wanted to walk 1 kilometer, right? So you walk, don't take the car, right? Unnecessarily you are just damaging the air. But that takes a lot of time. Because it should come from the education. It may take 20 to 30 years, but we don't know whether the world will survive or not if the situation continues like that. So that is one of the reasons why people are jumping into a clean energy technologies, and one of that type is a hydrogen. Why hydrogen? When it burns, it won't emit any CO2. It has got a high energy density. It can be stored without losing its energy. And you have a huge quantity of the resources, the seawater, that you can convert, if you have the technology, converts into hydrogen. But it has got a lot of unique properties and opportunities. But the current technology to produce the hydrogen is mainly coming from this natural gas, crude oil, or the coal. To produce 1 kg of hydrogen, people are generating 10 kg of CO2. But to meet our demand, it's almost 94 million tons of hydrogen that we need now. But in 2050, we need 530 million tons of hydrogen. If you use the existing technology, you can simply calculate 5,300 tons of CO2 will be liberated to the atmosphere. So, what are the current technologies? The green hydrogen production, which is mainly coming from the natural gas, right? But it's a crude technology, it emits a lot of CO2, right? And the cost is less, but you can't just use it. Yes, it's detrimental to the atmosphere or the air. Then people are jumping into green hydrogen production. That's the electrolysis of water. So use electricity to split water into hydrogen and oxygen. But the issue is you need high purity water and also highly expensive noble metal catalyst, because the cost of producing hydrogen is quite high. That's a major problem. Then people are jumping into photocatalytic production of hydrogen. That you can use the sunlight. But with the new photocatalyst. But the issue here is that with the current photocatalyst gives less than 1% solar to hydrogen conversion efficiency, which is not enough for the commercial production of the hydrogen with the lower cost. Even though we have huge quantity of the sun energy, but the efficiency of that material that is currently available is very poor. So we have the sun energy heating the earth is 885 million terawatt hour. We have enough energy, free energy that is available. But when they talk about hydrogen, they are not thinking about the source of water. This is a critical thing. Because to split the water through electrolysis, you need a high purity water. Right? But how much water we have in this world? So we have 333 million cubic miles of water. In that, 97% is a seawater. And only 0.3% is in the form of river, lake, or the glaciers or whatever. Even with that water, Tamil Nadu is fighting with the Kerala is fighting with Karnataka, and Kerala is fighting with maybe Andhra Pradesh. Every state is fighting because they don't have a water. If you start to use that river water or lake water for the electrolysis, and you are going to create another social problem. Because you need a high purity water. Because to produce 1 kg of hydrogen, you need 10 kg of water. But how much electricity do you need? To make 1 kg of hydrogen, you need 55 kilowatt hour energy. To convert 1000 liters of water, right? For example, so if you convert the sea water into normal water through the desalination process, you need 3.3 times more water anyway. And you need 5,500 kilowatt hour energy. That's a lot. Just to convert 1000 liters of water. To overcome all these drawbacks, and our center has been developing a new form of the catalyst so that can use the sun energy and split the seawater into hydrogen. And this is the technology, that's the groundbreaking technology that I'm going to present to you. But just producing hydrogen is only enough? No. Once you produce hydrogen, what you are going to do with that hydrogen? You have to generate energy. But to generate energy, you need another technology. That's a fuel cell technology. But fuel cell generates electrical energy. But then to use that energy, right, continuously, you may have to store it somewhere. Then you need energy storage devices. Right? So, what we need is an integrated approach of harvesting that energy from the sun and generate that energy and store it. And when the sun is there, you can generate those energy. But when the sun is not there, the sun will be there for only 8 hours. But after that, then you can use the stored energy for your purposes, the clean energy. And also, you need to also develop the technology to capture and convert that CO2 into a clean fuel using this material technology. So that is a device that we are developing at the University of Newcastle in my center, Global Innovative Center for Advanced Nanomaterial. So it is an integrated approach like fuel cell, photocatalysis, energy storage, and even the carbon capture and conversion. So if you can integrate everything, you can drive a car without gasoline or fuels, petroleum or diesel, just with the sunlight and seawater. What you need is this material. Right? Today in my talk, I'm going to show you how to make this fascinating material and how we can tune the electronic or electrical or semiconducting properties of the material to make it available for making this ultimate clean energy storage conversion device. So what is that material? It's a carbon nitrate. So carbon nitrate is the organic semiconducting material, which is a band gap of 2.7 electron volt. There are 5 different kinds of carbon-nitride: alpha, beta, graphitic, cubic and pseudo-cubic carbon-nitride. But among this carbon-nitride, the graphitic carbon-nitride can be synthesized in a lab in a large quantity. But other carbon-nitride, you need a very high pressure and temperatures to make it. You need a large quantity. You need a large quantity of the material if you wanted to make the device for the continuous production of energy. But with the high pressure technology, you can make only a few milligrams of the catalyst. That's not enough. That's not commercially viable. So that's what people are interested in, this graphite carbon-nitride. It has got a unique structure. The truth says triazine structure, but that can be synthesized by the chemical or molecular precursors at high temperature. We normally use this melamine or a cyanamide or a urea or thiourea. You heat it up to high temperature and then you take it out, check the performance of this material, and then you will get the semiconducting characteristics 2.7. But the problem with this material is that it has got poor specific surface area. Even though it has got a poor surface area, many people try to use this one because of this unique semiconducting property. It's mainly in CO2 absorption, because it's basic in nature, and with the just moisture you can convert that into methanol or methane, and then you can even use that as a photocatalyst for the degradation purpose or the hydrogen production. But the performance of the material is very poor because of the low crystallinity and low conductivity, and it's a fast electron hole recombination. So its band gap is 2.7, and that gives them only the limited visible light harvesting. So to overcome these challenges, so our center tried different approaches to improve the properties of this carbon nitride material by introducing the nanoporosity or changing the surface functional groups of this material to introduce the new property, or change the electronic conductivity of this material, or tune the band gap to introduce new characteristics, and then of course changing the ball structure from amorphous to crystalline, or even create the differences. By tuning or by adding these functionalities in your carbon nitride material, you can create a series of the material with unique characteristics, and that will be useful for the splitting the sea water into hydrogen. So that's what I'm going to show you in a couple of minutes, just one by one. First, how to introduce the nanoporosity in the system, and why do we need to introduce the nanoporosity? So in the bulk carbon nitride, the specific surface area of the material is very poor. It's less than 10 meters per gram. So what does it mean is that the number of the active sites in the material is very, very less. For you to get very high performance, the number of the active sites should be higher, right? By introducing the nanoporosity in the bulk carbon nitride, so you are increasing the specific surface area of the material. That's the one thing. The second thing is the ordered nanoporous channels can help you to enhance the mass diffusion and the rate of the reaction. That's the second characteristics. But the question is how to introduce the nanoporosity in the bulk material. That's quite simple by looking at this line, but it's not that simple. But templating strategy, right? Do you guys know templating? This is a simple way of making brick or a tiles or a toy. When you make a brick, you take wooden template, right? And in the wooden template, you put the clay, right? And remove the unwanted thing, and then heat it up to high temperature to strengthen the bonding, and then remove the template. Then you will get the structure of the template in your material. But when you wanted to change the size and shape, you change the size and shape of the template. Okay. Now imagine to bring down the size 100,000 times smaller and make a nano template with the nano channels. And in the nano channel, instead of clay, you put molecule with a small size and polymerize them, cross-link them, and then remove the template. So in this case, what we have done is we use highly ordered nanoporous silica template prepared by just a simple soap solution. That's a surfactant. So at lower concentration, it exists a monomer. At high concentration, it transforms itself into micelles in order to reduce the system entropy. We use that low-cost surfactant to make those template, right? And that creates a nanochannel. And we put that inside the nanochannel, introduce the carbon tetrachloride ethylene diamine, polymerize it, carbonate 600 degrees centigrade, remove the silica by sodium hydroxide, and you will get the structure of the template in your material, as you can see here. Can you see the prepared material has a highly ordered nanoporosity to the system, and the pores are arranged in a linearly fashion, and that gives a very high surface area, more than 500 meters square per gram. And the wall structure of the material you can see it's a pyridinic structure, but not just as triacin. Is the temperature we use is 600 degrees centigrade. The thermodynamic stability of the nitrogen in the carbon matrix is low. The nitrogen prefers to stay as a nitrogen molecule rather than making a bonding with the carbon. But the nitrogen content is low, but we call it as a black carbonate. It is a 20% of the carbon, and you can use that as a catalyst for the fuels. But to make a carbon nitrate with the C3 and 4, we change the molecule from carbon tetrachloride ethylene diamine to diaminotriazine. Why we use that? The diaminotriazine, you have a 5 nitrogen atom and 3 carbon atom. And it is a quite stable molecule. It's very difficult to decompose at a high temperature. So that the molecule will be available for polymerization and the cross-linking. And it doesn't have to, unlike this ethylene diamine and CCl4, it doesn't have to form the 6-membered ring or whatever. The membered ring is already there. So the energy that you need is less. So the low temperature, you can make those kind of triacin. So you see here, when you integrate this one with the templating, you can get a highly ordered and nanoporous carbon nitrate with the C3 and 4. Right? Because the decomposition of the nitrogen from the aromatic matrix, that is very difficult. And then you get the triacin structure with the yellow colored material. The band cap is 2.7 electron volt, and it has got very high surface area of 225 meters square per gram. So what about its structure after creating the nanoporosity? So if the structure is similar to the bulk carbon nitrate, so that has got this triacin structure, and we use that one for visible light photocatalysis, for splitting the water into hydrogen. But unfortunately, the performance of the material is very poor. You see here, the bulk carbon nitrate, it is less than 10 micromole of hydrogen, but if it's a mesoporous carbon nitrate with the C3N4, we got almost 300 micromole of hydrogen after 2 hours of this reaction. The reason for this poor performance is a less than 0.1% solar to hydrogen emission efficiency. The reason for this poor performance is that it's a limited visible light absorption. The light harvesting ability of the material is very poor. So to enhance that properties of the material, what we have done is that we try to change the molecular structure of this material from triazine to triazole. The triazine to triazole, that's a 6-membered ring to 5-membered ring, and you have 4 nitrogen atom and the 2 carbon atom. And we use the simple templating strategy to cross-link them in a confined matrix at a lower temperature. We were able to make a carbon nitrate with both triazine and the triazole, the 5-membered and the 6-membered ring. Right? And then you see that with a highly ordered mesoporous structure. And that gives very high surface area. From the electron-aerosol spectroscopy, you can see the CK and NK shell excitation edges, the intensity is quite high, meaning that the nitrogen content of the material is very high, and the bonding between the carbon and nitrogen is quite strong. It's a sp2 hybridized carbon. So one of the key features of this material is that, see, the C3N5, you have a large quantity of sp2 hybridized carbon as compared to the C3N4. Because CHN says that it is C3N5, but you can't have a triazine structure. Because that for the C3N4, right? And we use the triazole with the C3N5 stoichiometry, and you have a combination of triazine and the triazole, and the sp2 hybridized carbon is coming from here. And that significantly reduced the band gap of the material from 2.7 to 2.2. Right? And that's a significant reduction in the band gap of the material. And this is the world's first nanoporous carbon nitride with the C3N5 stoichiometry. And when we discovered this one, people thought that, oh, this material is quite unstable. It's an explosive material. And I mean, when you take it, it will just decompose. But we prepare this material at 500 degrees centigrade in the presence of the nitrogen. It is quite stable material with a very, very low band gap. And then we haven't stopped there. Then we ask the question to ourselves, can we make C3N6, N7, N8? But with the same chemistry, and you can't make the C3N5, you have to use a completely different chemistry. And in that case, to make a C3N6, we change the precursors from aminotriazole to aminoguanidine. The aminoguanidine, you see, you have one carbon atom and then 4 nitrogen atoms. And you need to put the 2 moles of the aminoguanidine to get that diamino tetrasin, and that undergoes polymerization, so you get the highly stable tetrasin-based carbon nitride material that has got the stoichiometry of C3N6. So we have made a new family of material like C3N5, C3N6 with a completely different molecular structures. What about how it changes the band gap? So when you change the molecular structure of the material, the band gap of the material also changes from 2.7 to 2.2 to 2.5, and then 2.25. Because the number of the layers under the structure of the carbon nitride in this C3N5 and N6 are completely different. Because the coupling of the layers makes a huge difference in the band structure of this final the material. So even the C3N6, we were able to get the highly ordered mesoporous structures when we integrate that one with the templating approach. So these are all the different ways of making a carbon nitride with the different stoichiometry by simply changing the chemistry, right? But then we can also make that one by changing the temperature of this material, right? So Professor Bawendi mentioned that the optimizing the condition is crucial to make the materials with a unique property that you need for different application, right? So in this case, we change the precursors from triazine to triazole to tetrazole. The tetrazole can be easily decomposed at a lower temperature so that it can easily make a bonding with the neighboring molecules to get new molecular structure. Change the temperature from 250 to 550 degrees centigrade, we were able to get C3N5, N6, N7 and N8. You see, as the temperature increases, the N-N bonding, the intensity of the bonding that increases quite significantly. And it's a real materials with a highly ordered mesoporous structure. And what about the structural stability? So how much time I have? So maybe I will speed up maybe 2 or 3 minutes. So the structure is quite stable, but then when you check that one for the hydrogen evolution, the performance increased from 300 to almost 800 micromole. But that's not enough for the commercialization. And to enhance the performance of the material, we change the conduction and valence bandage of the material by putting kind of different heteroatom into the system, like carbon or sulfur. Why we are doing it? But when we put the sulfur, we are creating the electron deficient center and then creating the dipole. Creating the dipole into the system makes a huge difference in the band structure of this material. As a result, you see the performance increased from 300 to almost 7,500 micromole of hydrogen per gram. how we are achieving that, the electron hole recombination is significantly suppressed when we did the work. So ladies and gentlemen, I am telling you how we can manipulate the properties of the material to enhance the performance of the material in the water scale. But all these materials are in the powder form. But what would happen if we change that framework structure from amorphous to crystalline? And how to make a crystalline framework? So we use the salt-assisted approach to force the molecule to react in a confined matrix to get the crystalline carbon nitrate framework. We use the potassium chloride or the sodium chloride or lithium chloride. When we use that, we could get the highly crystalline carbon nitrate material, as you see here. The crystallinity is quite high, right? But you can even introduce the mesoporosity by adding the silica nanoparticle. Surprisingly, the crystalline carbon nitrate material, the sulfur, but this is the sulfur doped system, with the normal water, it gives a 20,000 micromolar hydrogen, right? And to check the performance of the material at a different pH, we added some kind of sodium chloride solution into the system. But fortunately, when we change that one into normal water to salt water, even with the bulk carbon nitrate with a very poor surface area, we could get the 30,000 micromolar of hydrogen in the seawater, right? And but when you use this mesoporous carbon nitrate, we could increase from 300 to almost 54,000 micromolar of hydrogen. And this is the champion data in the world, right? And it is the dream of every scientist to split the seawater using visible sunlight. And it was, and people, struggling to achieve 0.1% efficiency. And we were able to achieve almost now 3.5% solar to hydrogen conversion efficiency. And ladies and gentlemen, this is going to change the world. And this is just visible light photocatalysis of splitting the seawater into hydrogen. And we haven't stopped there. We tested the seawater collected from the different beaches along the coastal line. We compared that one with the commercially available one, that is TiO2 photocatalysis, that gives only 2,400, and look at our system, it's a 54,000 micromolar of hydrogen per gram of the system, right? And seeing is believing. Without any electrical connection, you see that the hydrogen is coming with a very high speed. The rate of production of the hydrogen is very high with a just visible light. And we converted that into normal solar cell device. You see? From the complex system into a simple device that you can set it up in every household to produce hydrogen. Or every car that you drive. Once you integrate that with the fuel cell, you get the continuous cycle of energy. Right? But the cost of producing is also very high, very low, because the material that we used it's of low cost. And we did some kind of economical calculations. If you make this one in a 25 square kilometer, it will generate 64,000 ton of hydrogen with a market value of almost 6,500 crore. So ladies and gentlemen, so this technology requires only material, seawater, that's it. And you will be able to generate huge quantity of the hydrogen. In any petrochemical industries, aluminum smelting, green steel industries, and copper smelting companies, and like a solar panel, every household, you can keep this one for heating or cooling or electricity, and this is going to change the world. But if this is not going to generate any CO2 to the atmosphere. But this single technology is enough. Yesterday we had a wonderful discussion with the Moungi. Maybe not enough. Maybe we have to integrate that one with the fuel cell and energy storage and conversion. And that's what we have done. I think we don't have much time. And we even improve the performance to another 20% by modifying that one with the quantum dots. Right? To improve the conductivity of the material or the band edge of the material. And we can even get 5% or 7% or 8% by modifying that one. Right? But when solar cell was discovered, the efficiency was less than 1%. But now people are talking about 25%, right? And this is the early stage of the discovery. And we have every opportunity to increase the efficiency from 3.5 to even 5 or the 7% by just manipulating the properties of this material. So I think since time is running out, I will just end this one. And we have also developed the technology to convert that low cost, easily available waste material into nanocarbon. And the nanocarbons have a very high surface area, and that could absorb the CO2 of 2.2 ton CO2 per ton of the material. This is again the champion data in the world, and the absorbed CO2 can be converted into methane or even methanol by suitable catalyst. So if we can integrate this technology into this one, like seawater splitting and carbon capture into fuel, and in the fuel cell or the energy storage, you will be able to generate the continuous production of the energy. That's a clean energy. So what you need is the material, but if you have the material and with a unique property, and then you can develop new technologies, and that can touch the millions of lives, and that can change the world. That can make a huge impact to the society. So these are all the materials that we are looking for to save the world and help the society. So ladies and gentlemen, thank you so much. Thank you.